Welcome back to AE 2220 Dynamics. In this video, we're going to continue our discussion on kinetics of particles, Newton's second law, by going through example 2. In this example, we are given that a pendulum is connected to a moving cart with an inelastic wire. The cart moves without friction and is connected to the ground by a spring. Gravity is included, and it says here that x of t and theta of t are measured from static equilibrium, meaning that we don't need to worry about any unstretched lengths of the spring. And we are asked to determine the equations of motion governing the cart and the pendulum, the normal force supporting the cart, and the tension in the wire. This is a problem where the kinematics, or specifically the acceleration, is not something that you can directly derive or directly guess what it is just by looking at the problem. You could for maybe the cart, but the pendulum is not as straightforward as you might think it is. And as a result, we do really need to do the kinematics here. So we're going to start by choosing a coordinate system. We're going to, in this problem, we can pick our origin anywhere. A convenient place is to pick the origin at the fixed point or the grounded point of the spring. So we'll just write here A, origin at fixed point of the spring. So we'll put our origin here. We're going to then use a standard Cartesian. And you might wonder, why are we using Cartesian when we have rotation in the pendulum? Couldn't we use a polar coordinate system there? And the answer is yes, you could use a polar coordinate system fixed at the connection point between the pendulum and the cart, but then you will have a coordinate system that is translating as well, and you will need to account for that translation due to the cart moving, and as a result, you'll end up needing to deal with transforming that polar or radial and transverse coordinate system into a Cartesian coordinate system anyway. And as a result, it is easier if we just start with a Cartesian coordinate system to begin with, and then we'll use relative position vectors to describe the position of the pendulum with respect to the cart, and then use that to determine the actual position of the pendulum with respect to the origin. And we have an aside about this down here. Like I mentioned before, we could use these polar coordinates. It allows you to define this relative position vector in polar coordinates, but you're still going to have to take into that account, and you'll end up having to break this E hat R into Cartesian coordinates anyway, so we're still going to need to just deal with Cartesian. So we'll just start with Cartesian here. We'll have our I direction in the horizontal, and we'll have J in the vertical direction, as shown here. And then we'll have counterclockwise positive. So rotation in the counterclockwise direction, that's going to be positive. Let me draw a better rotation. That's our positive direction of rotation. We now want to define position vectors for the cart and the pendulum. Let's start with the cart. The cart is going to just go directly in the horizontal direction. We'll call this R sub C. The pendulum will go from the origin to the pendulum. We can call this R sub P. And then we're also going to use here a relative position vector from the cart to the pendulum. Let me correct that location right there. We're going to call this RP/C. So that is the relative position, or the position of the pendulum relative to the cart. That's what RP/C stands for. So RC, we can write as RC is equal to, we're going to need to add a dimension here. I'll call this A, to the position where the cart currently is, and so we'll get A plus X in the I direction plus 0J. This is very similar to what we had in the first example. And then we will need to now define our position of a pendulum, Rp. So Rp is going to be equal to first Rc plus that relative position P R sub P slash C. And then now you can see where this R slash P C comes from it. And we can use polar coordinates to define that. We get L is equal to E hat R. However, we were going to end up needing to break that up into Cartesian coordinates anyway. In fact, let's go ahead and let's just do that right here. So we're going to say R P slash C is equal to L E hat R. And I don't have any space to do it right here, so I'm going to go back up top and we're going to draw our position vectors. Here is J. Let me start by drawing straight lines. Alright, so this is I, the top one is J. At the angle here, this is E hat R, and then normal to that we have E hat theta, and then the theta angle is actually right here, which means that it's also right here. So if we can break up E hat R into components. We're going to find that if we come in and we draw our triangle here, the angle right there in green, that's theta. So E hat R is going to be equal to sine theta in the, we're going to do this in purple to distinguish from the side here. So E hat R is going to be equal to sine theta I. And then for the other term, we're going to have here, it's going to be minus cosine theta in the j direction, because it's pointing in the negative j direction. So we can now go ahead and we can expand this position vector for the pendulum, or this relative position vector, and we're going to get L sine theta in the I direction minus L cosine theta in the j direction. And then from here we can go and we can compute the position vector of the pendulum. Again, just to write it out, Rp is equal to Rc plus Rp slash C. So then we find that the position vector Rp is equal to the quantity A plus X plus L sine theta, all of that in the I direction, minus L cosine theta in the j direction. And the key thing here is that we now end up with an X in the horizontal position of the pendulum. And this is why we cannot just use polar coordinates, because if we only use polar coordinates, we would be missing this translation component. From here, we're going to go and compute the velocity and acceleration vectors. We'll start with the cart over here on the left. So the position vector was a plus x, so we're just going to get for r dot, we're going to get this is equal to x dot I plus 0j. We want to keep the zeros here, even if it's trivial, just because when we go and do Newton's equation, second law, we're going to end up applying it in the vector form, and we'll need to be able to split that up into components. So keeping the 0 here is convenient for that. This is rc dot, and then rc double dot is equal to x double dot in the I direction plus 0j. All right, so that is our cart. Let's now take a look at the pendulum. So we'll go and compute Rp dot. Because we're in Cartesian, we won't need to take derivatives of any unit vectors. And so we're going to get A as a constant, so we'll get rid of that. We'll get x dot plus L theta dot cosine theta. That comes from taking the derivative of the sine term. I'm just going to lower this a little bit, of that sine term, and then we pull out a theta dot from that as well. And this is all in the I direction. And you'll see that we've kept the x term plus, well, we're gonna have cosine, minus cosine. We take the derivative of that, we'll get minus sine times the negative, gives us positive. So in this case, we're gonna get L theta dot sine theta in the j direction. And then the acceleration vector rp double dot is going to be equal to x double dot. And now we got to do a chain rule or a product rule here for this next term. So we're going to get L theta double dot cosine theta minus L theta dot squared sine theta. That is in the I direction. And again, we're going to do a product rule in the j direction. In fact, I'm going to write that on the next line. So we're going to get plus, we're going to get L theta double dot sine theta plus L theta dot squared cosine theta in the j direction. Okay, we've now dealt with the kinematics. We now know our acceleration vectors, and this is a case where you would not be able to just look at the problem and guess what the acceleration vector is. Even if you were to account for this translation, you still would not be able to directly just write this out. This is why writing out position vectors explicitly and then computing velocity and then computing acceleration vectors is so important, because the kinematics is not straightforward. You cannot just look at the problem and guess what the acceleration and hope to get it right. Sometimes you might, for very simple rectilinear motion problems you might, but for general problems you very likely will not get that correct. All right, at this point we're now ready to move on and draw free body diagrams. We're going to start with our cart. I'm going to draw it right here. I'm just going to resize this square. This is our cart. We'll write cart up here just so we're aware. And then we're going to do the pendulum over here. Generally, I like to draw these so that the geometry, they make sense. So normally I'd like to draw my pendulum somewhere down here so that I can draw the tension forces appropriately. In order to save some space here, we are going to separate them. But it can make sense and it can help if you draw them out in their physical locations with respect to each other. That can help you to understand what force is corresponding to what other force on each body. All right, so for the cart, we first have our gravity force, which is big mg. We have some normal force that is acting on it, N here, the spring force. And if you're not familiar with spring forces, how to compute them, please let me know. I'll be happy to discuss this and either send out, likely I would send out a handout to help explain how springs work, as well as how dampers work in case you've never seen a damper. Be very happy to cover that. And then lastly, from the center, we have here a tension force through the wire. Tension is acting at an angle theta. If we come and draw the vertical component right here, and then the horizontal component right there, we know that this angle here is theta. So this term, the vertical term, is going to be T cosine theta. Oops, I actually left out the T. The tension force is T. That's what we'll write it as, capital T. So the vertical force is T cosine theta, and the horizontal force is T sine theta. So we broke this up into components because we're dealing with a Cartesian coordinate, standard Cartesian coordinate system. And so we broke this up into components to reflect that. Let's now go and look at our pendulum. Just go ahead and draw a circle here for the pendulum. I'm going to actually move that down a little bit. And for the pendulum, we have our gravitational force, mg, pulling down. Then we have the tension force pulling up at an angle. Which we're going to end up needing to break into components. All right, so this was our tension force T. It's pulling up on the pendulum. Got a vertical force here and a horizontal component with this angle. Oh, sorry. This angle right here is theta. So the vertical force is going to be T cosine theta, and this should match what we see for the cart, and it does. And then the horizontal force should be t sine theta. Perfect. And that is all we need for our free body diagram. From here, we can go and apply Newton's second law, which again is the sum of the forces is equal to the mass times the acceleration for each component. Let's start with the cart. So we'll write cart here. Again, we're doing this for each object. So let's start with our forces. In the I direction, we're going to have minus kx plus t sine theta. And that is everything acting on the cart in the I direction. And in the vertical direction, we have the n, normal force n minus gravitational force minus t cosine theta in the j direction. This is equal to m. And now we'll write out our acceleration vector, and it should be a big M, not a little m. Big M. And this is going to be x double dot in the I direction plus 0 in the j direction. And now we're going to split this up into components. Starting off with the I direction, we're going to get here, we'll get minus kx plus t sine theta is equal to mx double dot. From here we can go and solve and find the equation of motion. Mx double dot plus kx equal to t sine theta. So theta here is a coordinate, so generally we would want to put theta, any term with theta, on the left-hand side. For right now, we're going to leave it on the right-hand side because we're going to go and find the expression for the tension, and we're going to work to eliminate it from this equation such that we can find the underlying equation of motion and simplify, since t, or the tension, is an unknown of the problem as of right now. All right. So now that we're done here, let's look at what our equation in the j direction gives us. This is going to be t cosine theta minus mg. This will be equal to, oh whoops, sorry, I skipped ahead here. I was looking at the pendulum. So we're going to have, let's look at our forces here. We're going to have n minus big mg minus t cosine theta is equal to m, well, it's actually just equal to 0, so we'll just leave that as 0. So then we can write that our normal force N is equal to big mg plus t cosine theta, and we still don't know what t is, so we're going to end up having to find that. We're now going to move on to the pendulum, and what I'd like you to do is pause the video and go through and see if you can find the two equations for the I and j components, and then when you come back, you can check with what we end up in the example, and then we'll end up applying some algebra in order to separate the tension from the theta equation, and then solve for the theta, find the equation of motion for the pendulum, and then find the tension separately. All right, go ahead and pause the video and work on the pendulum. Okay, welcome back. We're going to go through the pendulum, looking at the different forces. So looking at our free body diagram here, we have, first, we have in the x direction, we only have minus t sine theta. So we're going to minus t sine theta. We're writing out the full vector equation. Plus, and in the vertical direction, we're going to have t cosine theta. And then minus little mg, that's all in the j direction. And this is equal to m little m times, and now we're going to go back up and look at our acceleration vector. You see that we have quite a large acceleration vector, and we need to incorporate all of those components. And this is why the kinematics is so important and so essential, and why you should really spend a lot of your time starting off with it is to deal with this, because it's much more involved than dealing with the forces generally. So we're going to get here the quantity x double dot plus L theta double dot cosine theta minus L theta dot squared sine theta. All that in the I direction. Let me just double check that real quick. Yep, minus L theta dot squared sine theta. Yep. Then plus, and in our J direction, we will have L theta double dot sine theta plus L theta dot squared cosine theta. That's all in the J direction, and that is the right-hand side. We're now going to go ahead and we're going to split this up into components. So we're going to do I first. We're going to get minus t sine theta is equal to m times the quantity x double dot plus L theta double dot cosine theta minus L theta dot squared sine theta. That's everything in the I direction. We could multiply by minus 1 and divide by sine theta in order to find the tension. However, the issue here is that if you sine of theta can sometimes be 0, and then you're dividing by 0, and therefore this kind of operation doesn't make sense or doesn't work. So we don't want to divide anything by a quantity that could be 0 at a given time. We're going to call this equation 1 here. And then now for the J component, we're going to get t cosine theta minus mg is equal to m times the quantity L theta double dot sine theta plus L theta dot squared cosine theta, and we're going to call that equation 2. Again, we could divide by cosine theta, move the mg over and then divide by cosine theta to find the tension. However, doing this again, cosine of theta could be 0 at a particular time, and as a result, we would end up dividing by 0, so that also doesn't work. Instead, what we're going to do in order to simplify this, and this is where dealing with trig and knowing your rules of trig and also algebra really helps out. What we're going to do is we're going to multiply equation 1 by the cosine theta, and we're going to multiply equation 2 by sine theta, and we're going to add the results together. Let's say add the results. All right, I'm going to write that again. We're going to add the results together. So we're going to end up here with minus t sine theta cosine theta, that comes from the first term, plus t sine theta cosine theta is equal to, left out, minus mg sine theta is equal to, this is going to be a doozy, but we're going to have m times square bracket x double dot cosine theta plus L theta double dot cosine squared theta plus L theta double dot sine squared theta plus L theta dot squared sine theta cosine theta minus L theta dot squared sine theta cosine theta, close square brackets. And we can go through and we can do some simplifications here. First, we can eliminate this t sine theta cosine theta term. Second, this quantity that I just drew the bar over, this is going to be L theta double dot. That's because cosine squared theta plus sine squared theta is equal to 1. And then lastly, we can eliminate these last two terms, such that we end up with m times L theta double dot plus mx double dot cosine theta plus mg sine theta is equal to 0, and that's going to be our equation of motion. We'll call this star. That's our equation of motion for theta. Later on, we're going to multiply by L to put it in a more standard form, and we'll see why as we continue through this analysis. All right, so we're now going to multiply. Let's just put a bullet point here, because that was a complete operation. We're now going to do another operation. We'll separate with that another bullet. So we're going to multiply here. We're going to multiply, in this case, 1 by sine theta by sine theta and 2 by cosine theta, and then we're going to subtract. The order of subtraction doesn't matter. You'll just end up with a negative sign that will end up canceling out. So we're going to subtract the results. Okay. So if we do that, we're going to end up with t times cosine squared theta plus t sine squared theta minus mg cosine theta is equal to m times square bracket with the quantity L theta double dot sine theta cosine theta minus L theta double dot sine theta cosine theta minus x double dot sine theta plus L theta dot squared cosine squared theta plus L theta dot squared sine squared theta, and we can close our square bracket here. Okay, we can go ahead and simplify further here. The first term here just becomes tension. On the right hand side, we can cross out the two theta dot terms, and then the last two terms we can combine into L theta dot squared. And then from here, we will end up with that the tension T is equal to mg cosine theta plus ml theta dot squared minus mx double dot cosine or sine theta. With this now, we can go and compute the normal force, and we can plug in for the tension there. We'll write then that the normal force is equal to N is equal to big mg plus mg little mg cosine squared theta plus m L theta dot squared cosine theta minus mx double dot sine theta cosine theta. And it may be possible to simplify the normal force, but we're going to leave it as this expression. We can then go plug the tension into our equation for x double dot, and we'll get m x double dot plus kx is equal to mg sine theta cosine theta plus ml theta dot squared sine theta minus mx double dot sine theta. That should be sine squared theta. And then lastly, we had ml theta double dot plus m x double dot x double dot cosine theta plus mg sine theta is equal to 0. We're going to call the equation for x double dot equation 3 and the one for theta double dot equation 4. So what we see here is, first of all, in the equation for theta double dot, we have this mx double dot cosine theta, and we would expect to see a similar term in the equation for x double dot, but instead of having x double dot cosine theta, mx double dot cosine theta, you would expect to find an m theta double dot cosine theta. And to that end, we end up with, we don't find that, but we do find a theta squared times x double dot. We generally want to avoid these mixed terms at the highest derivatives. Like, we don't want to have x double dot multiplied by a sine theta. And so we're going to want to do some kind of transformation to deal with that as well. And this will allow us to then put it in the form where we end up having the right equation for x double dot that does not include this mixed term and does include a similar term as that we saw in that theta equation. So we're just going to write here that we generally want to avoid mixed terms at the highest derivative. And then to avoid this, we're going to multiply 4 by cosine theta and add to equation 3. So will give us our proper equation of motion. And then lastly, we're going to, let me rewrite that. We're going to multiply, so lastly, we're going to multiply 4 by L. And this will put them in a, what we'll call a symmetric form for right now. All right, so dealing with that first operation, we're going to get here big M x double dot plus m x double dot sine squared theta plus little m x double dot cosine theta squared plus ml theta double dot cosine theta. Let me rewrite that L. My notes have sine theta times this term, but it should be a cosine because we multiplied by equation 4 by a cosine, so that's just a mistake in my notes. Plus mg sine theta cosine theta minus mg sine theta cosine theta minus ml theta dot squared sine theta plus kx, and that's equal to 0. And we can simplify this. This will become mx double dot, and then we can cancel out the gravity terms there. And then we'll end up with, for our equation of motion for x, we're going to end up with big M plus little m x double dot plus ml theta double dot cosine theta minus ml theta dot squared sine theta plus kx is equal to 0. For our equation of motion for theta, we have to multiply by L. We're going to get mL squared theta double dot plus mL x double dot cosine theta plus mgl sine theta is equal to 0. For the tension, we have that T is equal to mg cosine theta plus ml theta dot squared minus m x double dot sine theta. And then for the normal force, we have that N is equal to big mg plus mg cosine squared theta. And like I said, you could probably simplify this more. We're not really going to bother here. Plus ml theta dot squared cosine theta minus mx double dot sine theta cosine theta. And that is our two equations of motion, the tension in the wire and the normal force. I just want to point out that we multiplied equation 4 above by L so that we would end up with these terms matching, except they have different acceleration terms in them. We wanted these two terms to match. That tells us that we found the right form of the equations of motion. Okay, that concludes this video. In the next time we meet in class, we will go through a third example, and then we will go over friction.